So let's do an example of maximizing or minimizing an objective function. Let's say we want to find the maximum and minimum values of the objective function capital F equals 2x minus 3y given the following constraints. So we will have four constraints, the first of which will be 4x plus 5y is less than or equal to 28. And then the other three are very simple. So the next one is y is less than or equal to 4. Then x is greater than or equal to 0. And y is greater than or equal to 0. So we have this system of four inequalities making up the constraints on this objective function. And so the last two constraints here are so common because when you get to real-world applications, you're often dealing with non-negative numbers, only 0 or positive. So those are common constraints, okay? But let's get down to it here. If we want to maximize or minimize the objective function, we need to find the feasible region of this system of constraints. So we need to graph the solution set for this system of constraints. And to graph them, let's start with the first one. 4x plus 5y is less than or equal to 28. Since that's in standard form, the easiest way to graph it is going to be using intercepts. So let's plug in 0 for x. That means 5y equals 28. So y would be 28 divided by 5, which is the same thing as 5 3/5 if we want to graph it. Now let's plug in 0 for y, and we can see that 4x would equal 28, so x would be 7. Okay? Then we need to decide which side of this line to graph on. So we're going to use a test point 0, 0, so we get 4 times 0 plus 5 times 0 is less than or equal to 28. And well, the left side is 0, and 0 is less than or equal to 28. So we know we're going to shade on the 0, 0 side of this boundary line. Okay? The other three are very simple. We don't have to do any work for those at all. So let's go ahead and graph the constraints here. That didn't line up quite like I wanted. There we go. And let's put our x-axis in. So the first constraint goes through 0, 5 3/5. So we'll use a scale of 1 on the x and the y-axis. So 1, 2, 3, 4, 5 3/5 is a little bit more than halfway up there. So that's that point. Then 7, 0. So 1, 2, 3, 4, 5, 6, 7 is over here. And we'll graph this line. We have a solid boundary line because the inequality, in fact, all of these inequalities have equals in them, so they're all solid boundary lines. Now, because we have so many boundary lines, let's go ahead and label this one as 4x plus 5y equals 28. And let's go ahead and state that we need to shade the 0, 0 side. So we're shading below this line. You could even write below there if you prefer. Okay. Now y equals 4 is a simple boundary line. So y equals 4, so 1, 2, 3, 4, there's 4. So we get this horizontal boundary line, y equals 4. And we don't have to use a test point. We can just see that, well, this says y is less than or equal to. So the less than part tells us to shade below. So at this point, if we're shading below this line and below this line, then we're talking about our feasible region at this point is everything in this section. Okay? All right, then x is greater than or equal to 0. Well, x is 0 right here. So our boundary line actually is the y-axis, x equals 0. And since it's x is greater than or equal to 0, the greater than tells us we'll shade to the right of that boundary line. Shade to the right. So that means now the region we had before was all of this, but we're only shading to the right of the x equals 0 line, so we have this. Okay, not this triangle here, because we have to be below the y equals 4 line, so we're looking at this so far. Okay, next we have y is greater than 0, which is actually this horizontal line at 0. So that's y equals 0 as our boundary line, and it says y is greater than or equal to, so we'll shade above this guy. So now our feasible region happens to be this quadrilateral. It's closed now. Right, when we satisfy all of those conditions, we're looking at this guy here, which has 4 corners. 4 corners, 4 vertices. So A, B, C, and D. Now, this guy up here is not a vertex because it's not a corner of the shaded region, even though it intersects another boundary line. So don't make that mistake. That is not a vertex. The vertices are the corners of your feasible region only. So now we need the vertices. So let's see, vertex A, we can tell by looking at the picture that the vertex A is 0, 4, so that's easy. We can also tell, let's see here, vertex B looks like it might be 2, 4, but this line here, this slanted line, had this ugly y-intercept of 5 3/5, so let's not assume that's 2, 4. Let's find vertex B. Let's find vertex B. So vertex B is where the slanted line intersects the horizontal line y equals 4. So the system that we have is 4x plus 5y equals 28, and then the other equation is y equals 4. The good news is this is very easy to solve by substitution because we already know what y is. Y is 4. So all I have to do is plug that value in for y to the first equation. So we get 4x plus 5 times 4 equals 28, which means that 4x plus 20 equals 28. Then we subtract the 20 and we divide by 4 to get x equals 2. So vertex B is where x is 2, where x is 2, and y, we already know y is 4. So it does happen to be 2, 4. So, but it didn't hurt to be sure of that. Okay. Now I'm using, perfectly straight lines and all of that, and I still wasn't confident that that was exactly at 2, 4. So we got vertex A, vertex B, vertex C is clearly 0, 0, and vertex D is also, we already know it's 7, 0. We plotted it right there. I believe 7, 0. 1, 2, 3, 4, 5, 6, 7. Yep. So we only really had to solve for one of the vertices in this case. The other 3 were obvious. And now, as we know, when we're maximizing or minimizing an objective function, we just have to plug those 4 vertices into the objective function to find the max and min. Okay? So we have f equals 2x minus 3y. Let me confirm that one more time. F equals 2x minus 3y. Good. So now, if I plug in our vertices, let's start with vertex A, which is 0, 4. If I plug in 0, 4 to this guy, I get f equals 2 times 0 minus 3 times 4, which is 0 minus 12 is negative 12. Then we'll plug in the other vertices as well. Let's plug in the vertex 2, 4. I get f equals 2 times 2 minus 3 times 4, which is 4 minus 12, which is negative 8. We'll plug in 0, 0. That one's pretty easy. F equals 2 times 0 minus 3 times 0. So f is 0 in that case. And last, we get the vertex 7, 0 that we plug in. So we plug in 7 for x and 0 for y. So 2 times 7 minus 3 times 0. Well, that's 14 minus 0, which is 14. The directions said find the maximum and minimum values. So we have to do both in this problem. So in this case, the lowest value, the lowest output of our objective function is negative 12. So negative 12 is the minimum value of f. okay, on the constraints that we had. And in fact, if you wanted to write it occurs at the vertex 0, 4, you could write that, but the problem didn't ask, so I'll leave it alone. The biggest output of our objective function with these constraints is 14. So 14 is the max value of the objective function f, and that occurs at the vertex 7, 0. But that's all there is to it. We have our max and min values. It's a lot of work. You need to be good at graphing, you need to be good at finding intercepts, need to be good at solving systems, etc., etc. And then once you get, but the big idea is get the vertices, plug them into your objective function, and then find the highest and lowest values.